Last time, we learned how to control the angles of the servos in this 2 degree of freedom manipulator. Now, as we watch this 2 degree of freedom manipulator move, I'd like to point out something about the way the end effector moves through the robot workspace. Every time a servo moves, 2 things change about the end effector: its position and its rotation or its orientation. For example, in this position here, the end effector is located at one XY position in the base frame, and it's pointed in a particular direction like this. But after the servos move, the end effector is now located in this different position in XY space, and it's also pointing in a different direction. In robotics, we care about both of these things, the position and the rotation or orientation of the end effector. You can see why this is if you think about a characteristic application of robotics, such as painting. If you were using this robot manipulator to paint, you would not only care that the paint is applied at the right position, but you would also care that the spray paint can is pointed at the thing you want to paint and not pointed in some other direction. In the study of robotics, we have a particular way to represent each of these things: positions and rotations. We represent positions using something called a displacement vector, and we represent rotations using something called a rotation matrix. Today we're going to address rotation matrices, and next time we're going to be looking at displacement vectors. In order to explain rotation matrices, I have to first make sure that you understand the concept of a projection. If you've taken a class in linear algebra, you would have seen this concept before, so I'm just going to review it here. Suppose that I have an XY frame, as I've shown here. Now, suppose that I have an arrow pointing in some direction within this frame, like this. This arrow might represent, for example, the arrow that I drew previously pointing out from the robot end effector. Now, imagine that I would shine a light from above like this. The shadow of the vector would fall on the x-axis like this. The length of this shadow cast upon the x-axis is known as the projection of this vector on the x-axis. I could do the same thing from the other direction. Shine the light from over here. Now the shadow cast by the vector on the y-axis would be the projection of the vector on the y-axis. Now, suppose that I want to have some way to represent the direction that this vector is pointing in. One obvious way to do this would be to just write out the angle theta that defines the angle between this vector and the x-axis. Another way to do it would be to write out the projection of the vector on the x-axis and the projection of this vector on the y-axis as a vector like this. If I know this vector telling me the projection on x and the projection on y, I could back calculate the value of the angle theta by using the tangent like this. Now, in robotics, we are generally not working in 2-dimensional XY space like this. We're actually working in 3-dimensional XYZ space, but this idea of projections works in 3-dimensional space the same way it works in 2-dimensional space. The only difference is that we would have another number here, the projection of the vector on x, the projection of the vector on y, and the projection of the vector on z. Throughout robotics, we'll be using this idea of projections rather than the angle representation, because it will end up simplifying our math when we end up having many rotations in three-dimensional space. Now, in our robotics calculations, we're generally not looking at the rotations of just one vector in three-dimensional space. Instead, we're looking at the rotations of one frame inside another frame. In other words, we have three vectors that are rotating together, an x, y, and z vector. Let me show you what I mean. Suppose that I have a frame called frame 0, like this. And suppose that I have another frame called frame 1, like this. Now, suppose that initially frame 1 is lined up exactly with frame 0. Then, suppose that I rotate frame 1 like this. How could I represent the rotation or orientation of frame 1 inside frame 0? I could use this same projection idea. I'll start with the axis x1, and I'll write down the projection of x1 on x0, the projection of x1 on y0, and the projection of x1 on z0. Now I'm going to make another column next to this one. In this column, I'll write down the projection of y1 on x0, the projection of y1 on y0, and the projection of y1 on z0. Finally, I'll make a third column. In this third column, I'll write the projection of z1 on x0, the projection of z1 on y0, and the projection of z1 on z0. This 3x3 matrix of numbers has a special name in robotics. It's called a rotation matrix. We would say that this rotation matrix is equal to R01, like this, because the rotation matrix that we just wrote tells me how frame 1 is rotated inside of frame 0, or relative to frame 0. Now, so far, I've just been leaving blanks in each of these places inside the matrix. Is there a way that we could get actual numbers in each of these places? It turns out that there is, and it's pretty simple to do. In order to get numbers in each of these places, you first have to understand something about frames. In a coordinate frame, each of the individual axes is assumed to have a length of 1. Knowing that, could we figure out what numbers go in each of these places for this rotation that I showed as an example here? Suppose that I know the angle that we have rotated frame 1, and let's call that angle theta. Let's start with this first column. For the first column, we look at the x1 axis, and we project x1 onto x0, y0, and z0. Let's use what we know about sines, cosines, and tangents. Now, the cosine of theta is equal to the adjacent side over the hypotenuse. So the cosine of theta is the projection of x1 on x0. The sine of theta is equal to the opposite side divided by the hypotenuse. And in this case, the hypotenuse is always a length of 1, because the axes in a coordinate frame always have a length of 1. So that means that the projection of x1 on y0 is the sine of theta. I'll write that in this rotation matrix because this is the position that represents the projection of x1. What about the projection of x1 on z0? The projection of x1 on z0 is 0 because the axis x1 doesn't overlap the z0 axis at all. In other words, x1 is perpendicular to z0, and so the projection is 0. Next, let's look at the y1 axis. First, note that this angle here is also theta. We can use that information to figure out the projection of y1 on the 0 frame. The sine of theta is equal to the opposite side over the hypotenuse. The opposite side is the projection on the x0 axis. But notice that this is in the negative direction. The projection of y1 on x0 is negative. Now, the cosine of theta is equal to the adjacent side divided by the hypotenuse. The adjacent side is the projection of y1 on y0. I'll write that in this position in the rotation matrix. Lastly, what is the projection of y1 on z0? y1 is perpendicular to z0, so the projection of y1 on z0 is 0. I'll fill in the 0 in this part of the matrix. Lastly, let's look at the z1 axis. z1 is perpendicular to both x0 and y0. That means that the projection of z1 on x0 and y0 will both be 0, and I can fill in zeros in these places in the matrix. What's the projection of z1 on z0? Since the length of z1 is 1, and z1 lines up exactly with z0, that means that the projection of z1 on z0 is 1. I'll fill in 1 at this place in the matrix. Now, this matrix will correctly tell us all of the projections that we need for any angle theta that we might use to rotate the one frame in such a way that z1 does not change. Notice that in this rotation we made, we were rotating around the z-axis. In other words, the z-axis is the one that didn't change at all. This matrix that we derived here is known as the z rotation matrix. As long as we're rotating around the z-axis, this matrix will tell us all of the projections for any angle theta rotated around z. Now that we've derived this matrix, we don't need to derive it again every time we have a rotation around z. We can just plug in the angle theta that we've rotated and get all of the right numbers. We could do the same thing, deriving matrices for a rotation around x, where the x-axis stays the same, or for a rotation around y, in the case where the y-axis stays the same. I'm not going to do those derivations right now. I'm just going to show you what the answer is. The derivation is done in the exact same way that we derived the matrix for a rotation around z. Now, you may know that not all rotations consist of just a rotation around x, or just a rotation around y, or just a rotation around z. For example, suppose that I have one frame rotated relative to another frame like this. This rotation is not a rotation just around one axis. It's some combination of other rotations. So how could we write a rotation matrix for some arbitrary rotation like this? Well, it turns out that any rotation you can dream up is some combination of rotations around x, y, and z. Let me show you an example. Suppose that I took my one frame here and I rotated it 45 degrees around Z, like this. Now, suppose that next I make a rotation of 45 degrees around my new x-axis, that is the rotated x-axis, like this. I could write the rotation matrix for this rotation by first taking my standard form of a rotation matrix around Z, plugging in the number of degrees that I rotated around Z, and then multiplying this by the matrix for a rotation around X, and plugging in the number of degrees I rotated around X. When I multiply these two matrices together, the numbers that come out will tell me the projection of X, Y, and Z1 on X, Y, and Z0 without me having to actually derive the whole matrix. We can string together any number of a sequence of rotations like this, combining rotations around X, Y, and Z. Now, let's go back to the kinematic diagram that we drew for this manipulator that we built. We want to find out the rotation matrix that tells us how the end effector frame is rotated relative to the base frame. Since I know that we can string together rotations that happen one after another, I could find the rotation from the base frame to the end effector frame by first finding the rotation matrix from the base frame to the first frame, and then finding out the rotation matrix from the first frame to the second frame. Or another way to say this same thing is to say, I want to find the rotation matrix representing the rotation of the end effector frame relative to the base frame. I can do that by first finding the rotation of the one frame relative to the zero frame, or the one frame in the base frame, and then finding the rotation of the end effector frame in the one frame, and just multiply these two together. So let's see if we can find the rotation matrix from 0 to 1. As the first joint moves, the first frame, the one frame, is going to rotate like this. Now, don't be thrown off by the fact that the one frame is located in a different place or a different location than the zero frame. We'll be dealing with positions later in the section on displacement vectors. For the rotations, it doesn't matter at all that the frames are located in different places. We're only considering how the frame is rotating. As the first joint moves, frame 1 rotates around the z-axis. In other words, the z-axis stays the same as this rotation occurs. It's only the x and y axes that change. So that means that we can represent this rotation by getting the standard form of the z rotation matrix and using it. For the angle, we'll plug in our joint variable, theta 1. Theta 1 is the amount that we are rotating the one frame relative to the zero frame. Now, our rotation matrix 0 to 1 here isn't complete yet. There's another piece of the rotation matrix that we need to multiply on. I need to left multiply this matrix by another matrix that tells me how frame 1 is rotated relative to frame 0 when the joint angle is 0. Now, in this case, the rotation of frame 1 relative to frame 0 when the joint variable is 0 is no rotation at all. You'll see that in the kinematic diagram, x1, y1, and z1 are all in exactly the same directions as x0, y0, z0. There's a special matrix that means no rotation. and that matrix is the identity matrix. You can kind of see why this is true. This matrix tells me that the projection of x1 on x0 is 1, and the projection of y1 on y0 is 1, and the projection of z1 on z0 is 1. In other words, there is no rotation. I multiply these two matrices together to get me the complete rotation matrix from frame 0 to frame 1. Next, let's do the rotation matrix from frame 1 to frame 2. When servo 2 moves, frame 2 is going to rotate like this. Once again, this is a rotation around the z-axis. So I'll go and get the standard rotation matrix for a rotation around z. This time I'll plug in the second joint variable, theta 2. Now I need to left multiply this matrix by another rotation matrix that tells me how frame 2 is rotated relative to frame 1 before the joint variable moves at all. And once again, this rotation matrix is going to be the identity matrix because there is no rotation between these two frames before the joint variable starts to move. Lastly, I can find the complete rotation matrix from frame 0 to frame 2 by multiplying these two rotation matrices together. Let's do an example to see what this rotation matrix means for our physical manipulator that we've built.